So in this video, we are going to discuss about the Arrhenius equation. Arrhenius equation. Firstly, we will understand it in the simple terms what this equation wants to say. Okay, in simple meaning. See, for example, let's suppose A plus B giving rise to C plus D. This reaction is happening. Okay, and let's suppose that this reaction is happening at 30 degrees Celsius. Okay, and that time its rate is around X. Okay, this reaction is happening at 30 degrees Celsius and its rate is X. Okay, now if we increase this temperature by 10 degrees Celsius, the same reaction is happening, A plus B giving rise to C plus D. But this time I have increased the temperature by 10 degrees Celsius and temperature over here now is 40 degrees Celsius. Okay, then now its rate that will be 2x. What is the conclusion? The conclusion is that this equation states that for any chemical reaction, by 10-degree increase in the temperature, the rate of the reaction doubles. Okay, by 10-degree increase from 30 to 40, I have gone 10-degree increase is there. Okay, so with the 10-degree increase in the temperature, the rate of reaction doubles. Okay, this is stated by the Arrhenius equation. I'm writing it over here. For any chemical reaction, the rate of reaction doubles if its temperature is increased by 10 degrees Celsius. Okay, if the temperature increases by 10 degrees Celsius, the rate doubles. Okay, this is what this equation states in simple terms. Now we will understand its mathematical concept. Mathematically, it says that this rate of reaction that is equal to A E minus EA upon RT. Now, what is A? A is the Arrhenius factor. Okay, A is called as the Arrhenius factor, which is also called as pre-exponential factor and frequency factor. Also called as frequency factor or pre-exponential factor. Okay, and this EA is the activation energy. This we have already discussed in our previous videos, that what is activation energy? Activation energy is the energy which is required to start any chemical reaction. Okay, and R over here, it is the gas constant, and T is the temperature at which this reaction is happening. Okay, by that we will calculate this K, that is rate of the rate constant. Okay, now when we will solve this equation, okay, that firstly at temperature T1, the rate was at temperature T1, the rate was K1, and then at temperature T2, the rate was K2. Okay, by solving this equation, we get log K2 upon K1 equal to EA upon 2.303 T2 minus T1 upon T1 into T2. Okay, this expression is very, very important, and every time from the past 7 years, every time one numerical is always asked from this relation. Okay, from this formula, one numerical is always asked from the past 7 years in the CBSE. Okay, so please understand this once again. What is this? This is temperature T1. At that time, there was the rate constant K1 of the reaction. Now the same reaction, when undergoes the increase in the temperature and it goes at temperature T2, then its rate constant is K2. Okay, and what is the relation between them? That is log K2 upon K1. Okay, K2 is that rate constant and temperature T2, and K1 is the rate constant at temperature T1. That is equal to activation energy. EA is the activation energy upon 2.303 into T2 minus T1 upon T1 into T2. Okay, T1 is that initial temperature and T2 is that final temperature which is changed. Okay, so this one is very important. So please learn this. Okay, if we discuss its graph, that what is the graph that we will get? So that is this. Okay, now this graph is at t plus 10 and this graph is at t, because I said that by increasing in the temperature the rate will increase, so this graph it will shift downward. Okay, this is at temperature t. Okay, now this is at temperature t plus 10, means the rate has increased, so that's why the graph has shifted downwards. Okay, so this rate of equation, this we have discussed about the Arrhenius equation, very important.